Well, it's 5 p.m. here in the UK, 4 p.m. UTC. So welcome everyone to another session of Flower Monthly. I'm gonna first share my slides to provide the agenda and a quick update about Flower. As you know, we run Flower Monthly every month on the first Wednesday of every month, and today is the first Wednesday of August, hence the Flower Monthly event. So the agenda, as usual, follows the same structure. This is the agenda. I'm gonna present it now. Then I'm going to be giving a quick update about some exciting new features about Flower. Probably most of you already saw that early at the beginning of the last week, we shared a new update of Flower with some quite exciting new features. So I will dive into some of those in just a bit more detail. And then we'll jump straight into our speaker sessions. We are very lucky today to have three super interesting speakers, one from Priyanka Das from the University of Texas at Dallas, from Jan Ritting from EPFL, and from William from our team in Flower Labs. So without further ado, let's jump on to the Flower update. So as I mentioned, the big update this month has been the release of Flower 1.20, which has two big features, which are the culmination of a couple of months worth of work. We did a huge refactoring on the communication mechanism and the whole communication and serialization stack in Flower, which now allows you to federate workloads as big as you want. This means that you can federate models no matter their size. If it's a tiny XGBoost model with a few thousand parameters or the biggest LLM you can think of, you can now federate it with Flower. And when we were stress testing the system, I set up a federation with 5 supernodes, which are the equivalent to clients in Flower, in 5 different countries in Europe. And I set up a Superlink, which is like the server that does the aggregation and coordinates the federation. I set it up in Germany. And I was able to see some pretty huge speedups. I was not only able to just do the federated pre-training of a 8 billion LLM, but also thanks to some of the new features, such as built-in broadcasting and streaming of large weights. The upload bandwidth from the server app to the Superlink was reduced by the number of supernodes involved in every round, in this case 5x. That's a big communication saving. And thanks to the streaming, which means the moment one node starts communicating the model, the other nodes that are supposed to receive it can start pulling it. It doesn't have to, the communication is pipeline, which means you don't have to complete the upload before the others can pull. And that allows us to see a measurable almost 3x workload reduction, which all this means that most of your time now is much more of your time is spent doing training in your GPUs, for example, or doing the processing of the local data and not on communication. So these are the two flagship features in Flower 1.20. All this comes transparently to you, so all your apps you have already been developing can benefit from these two features, and you don't have to make any changes to your code. And in addition to this, there are also a number of refactorings and fixes to make the system more reliable. And you can go and check the release blog post we made for Flower 1.20 to see this in a bit more detail, as well as other features that are in the release. And as always, you can upgrade with pip install -u FLWR. So this is a quick overview of the main update I wanted to share with you today. If there are some questions, either on Zoom, on X, on YouTube, or even on LinkedIn, please add your questions there and I will be answering later. So with this out of the way, let's jump into the first talk. The first talk is titled Federated Learning for Skin Cancer Detection with the HAM 10,000 dataset. That's a cool name. And it's going to be given by Priyanka Das from the University of Texas at Dallas. So Priyanka, the floor is yours. I'm going to stop sharing my screen and you can share yours.
Okay. Can you see my screen?
Yes, perfect.
Okay, so hi everyone. This is Priyanka Das, and I recently completed my master's in business analytics and artificial intelligence from the University of Texas at Dallas. Today, I'll present my project titled Federated Learning for Skin Cancer Detection using CNNs. This work explores how we can train deep learning models across multiple simulated hospitals without sharing patient data using a privacy preserving approach called federated learning. So let's dive into why is this used in healthcare. Um, so, as we all know, that healthcare data is highly sensitive. Centralized training methods often require aggregating data in one location, which raises serious privacy, legal, and ethical concerns, especially under regulations like HIPAA and GDPR. So, this is where federated learning or FL comes in. Instead of moving data, FL brings the model to the data. It enables collaborative learning across hospitals or institutions where sharing raw patient data without sharing raw patient data. Another key reason FL is well suited for healthcare is that the data is inherently non-IID. So, what is non-IID? So, non-IID data stands for non-independent and identically distributed data, a situation where the data varies significantly across different sources of or clients, both in distribution and characteristics. So, non IID means that the data is not randomly or evenly distributed. Each client or hospital may have different classes, different frequencies, or biases in the data. So, different hospitals serve different demographics and use different equipment and protocols, making centralized training model prone to bias and poor generalization. Um, let's move to the next slide. So, let me give you a quick overview of the project setup. So, my main objective was to train a CNN based classifier to detect different types of skin lesions, particularly distinguishing benign from a malignant without ever sharing the patient data. So, I used the HAM 10,000 dataset, which contains over 10,000 dermatoscopic images across 7 diagnostic categories. So, as you can see on the right hand side chart, there's a heavy class imbalance with the majority labeled as NV and much fewer samples for rare conditions like VASC or DF. So, to simulate the real world condition, I created a federated environment with 5 virtual hospitals using the Flower framework, where each hospital was treated as a separate client. I introduced realistic non-IID partitioning, meaning each hospital had its own class imbalance. This simulates the real-world scenario where different regions or hospitals see different types of patients. The model was lightweight CNN with 3 convolutional layers and ReLU activations. I applied standard pre-processing steps like resizing, normalization, and tensor conversion. For training, I started with the FedAVG as the aggregation strategy, but later moved to FedOPT to better handle the challenges posed by the non-IID nature of the data. So I had created actually two programs, one for the Fed AVG, and then I saw that there was heavy overfitting and class imbalance. So that is why I opted for Fed OPT, and I also implemented oversampling there. Um, so this is the architecture of the federated learning. So you must be already aware of the architecture. Um, Now moving to the next slide. This is, let's talk about the data set. So for this project, I used HAM 10,000 dataset, which stands for Human Against Machine, with 10,000 dermatology images. It contains 10,015 dermatoscopic images across 7 classes of skin lesions, both benign and malignant. These images were collected from Austrian and Australian dermatology centers, making it a strong benchmark for automated skin cancer classification. The 7 classes include melanocytic nevi, melanoma, benign keratosis, basal cell carcinoma, actinic keratosis, vascular lesions, and dermatofibroma. One major challenge is class imbalance. The NV class dominates with nearly 67% of all images, while some rare classes have fewer than 150 samples. To simulate a real world federated setup, I divided the dataset into 5 clients. On the right side, you can see some sample images from the dataset. This gives a visual sense of the diversity in skin lesion appearance and across dataset. So here I'm again showing you, like I already discussed, that NV class has almost 65% of the data. So this non-IIT distribution led to two major issues during training. One is overfitting to the majority class, and the second is like poor generalization on minority classes. To mitigate this, I applied random sampling at the client level. This involved duplicating samples from underrepresented classes within each client's training data to balance class distributions. Importantly, I left the validation and test sets untouched to preserve a realistic evaluation scenario. Upsampling had a significant impact. It improved the model's ability to learn features for all classes, especially the rare ones. It also boosted the performance like accuracy and helped reduce bias towards the dominant classes. Now let's look at the CNN architecture I designed for this project. The table on the left outlines the layers and their roles. The input is 224 into 224 RGB image. I use 3 convolutional layers, each followed by a ReLU activation to introduce non-linearity. After each convolution, I apply max pooling to progressively reduce spatial dimensions and extract the most significant features. After the convolutional layers, the output is flattened into a 1D vector and passed through a fully connected layer with 128 units. And finally, to the output layer with 7 nodes, one for each skin lesion class. I didn't add a softmax here because cross entropy loss in PyTorch expects raw logits and handles that internally. The visual on the right side show two perspectives. The top diagram simplifies the flow, that is convolution to pooling and then flattening and then finally classification. The bottom diagram gives a more technical view, showing how the image shrinks in size while the feature depth grows, similar to how my model extracts hierarchical patterns from lesion images. Uh, Once the data was distributed to clients, each hospital's dataset was split into training, validation, and test sets, with 80% for training and 10% each for validation and test. Um, these splits were stratified to maintain the original class distribution, and importantly, upsampling was applied only to the training set to balance the class representation. The validation test sets remained untouched to ensure fair evaluation. In terms of evaluation metrics, I tracked accuracy and loss per round per client to observe learning progression and detect any overfitting or divergence. And also macro averaged accuracy, which is especially important due to the heavy class imbalance. This ensured performance was strong not only on the majority class, but also on the rare skin lesion types. So this is for the first experiment where I used the strategy of Fed AVG. So I trained the model across 5 simulated hospital clients for 5 communication rounds. The entire training took around 19.7 minutes. If we look at the global loss history, we see a steady decline from 0.0304 in round 1 to 0.0143 by round 5, indicating consistent learning. Similarly, global accuracy improved from 66.86% in the first round to 83.47% by the final round. This shows that even with non-IIT data, the client level variation Fed AVG achieved stable and effective convergence. On the right side, I have summarized the per client surface plot results. The accuracy surface plot showed an upward trend across all clients, with final accuracies between 83 to 84%. The loss surface plot showed a smooth decline starting from around 0.85 to 0.033, indicating a convergence stability. So I want to show you the plot. So this was the plot, and as you can see, it started from as low as 0.66 and it went as high as 0.83. So this was the highest. Um, so this is for each round for each of the client. This was the accuracy. Now coming to the second experiment, which I was using the FedOPT strategy. And here also the training ran for 5 communication rounds and it took about 21.4 minutes. Starting with the global loss, we observed a faster and smoother convergence, dropping from 0.0543 in round 1 to just 0.0101 by round 5. This is notably more efficient than what we saw with FedAVG. For global accuracy, FedOPT showed a steep rise from 37.24% in round 1. It climbed to 89.68% by the final round, outperforming FedAVG throughout. On the client level, the 3D surface plot gives us a visual confirmation. Accuracy curves are smoother and more stable across clients. All clients consistently improved with accuracies ranging from 37% to 89%. The learning paths show less fluctuation, meaning FedOPT handled non IID variations better. The loss surface plot also shows a clear drop from around 0.83 to 0.29, and importantly, it was more stable across rounds. These trends suggest that FedOPT not only accelerated convergence but also maintains synchrony among clients, which is crucial when data is heterogeneous. So for FedOPT, uh, this was the validation accuracy. So it started with 0.36 and it went to as high as 0.90 and 0.93. So for in case of Fed AVG, it never passed like above 0.90. This is one, and this is the training and validation loss plot. So I did this to check if it is like overfitting. So this is for the training loss and this is the validation loss. So as you can see that it is almost similar. So we can say that there is no overfitting here. Okay. So here I present side-by-side comparison to the two federated strategies, FedAVG and FedOPT, to summarize their performance. Starting with training duration, FedAVG completed in around 19.7 minutes, while FedOPT took about 21.4 minutes, just 1.7 minutes more. But this small increase in time gave noticeable gains. Final global accuracy improved from 83.47% with FedAVG to 89.68% with FedOPT. And the global loss dropped further from 0.143 to 0.0101. In terms of stability, FedAVG showed moderate variance in accuracy across clients, whereas FedOPT achieved more consistent learning across all clients. For loss convergence, FedAVG had a gradual and stable decline, while FedOPT offered a faster and smoother drop, especially in early rounds. So when it comes to client synchrony, FedOPT again performed better, showing tighter alignment between clients even in the presence of non-IID data. Overall, FedOPT outperformed FedAVG across all major metrics: accuracy, loss, and learning consistency. It also handled data heterogeneity more robustly, making it more suitable for real-world federated setups. That said, FedAVG remains a strong baseline. It's simpler and more computationally efficient, which can be helpful in constrained environments. So the choice between the two depends on the application, whether you prioritize efficiency or robustness. And I think I have a slide for that as well. So this one is for FedOPT. As you can see, it started quite low with 0.41, but it went higher till as high as 0.94. And this one was for FedAVG. So it started at 0.66, but it ended at 0.83, which is lower than FedOPT. So moving on to the next one. To wrap up, let's go over some of the key lessons learned and limitations of the study. So these were the lessons learned. First, I found that handling non-IIT client data is absolutely critical. Hospitals had different data distributions, which greatly affected model performance. Upsampling did help, but it required careful tuning. It is not a one-size-fits-all solution. Secondly, client level upsampling before training improved generalization. By locally balancing the class distribution, I was able to boost fairness and recall, especially for underrepresented lesion types. Third, I observed that lightweight CNNs work surprisingly well in federated settings. The compact CNN performed effectively without requiring large resource intensive models, which is great for low resource edge services. Lastly, FedOPT turned out to be better suited for real world heterogeneity. Its adaptive nature led to more stable convergence and slightly higher accuracy than FedAVG, making it ideal for non IIT medical data scenarios. Limitation and challenges. So, one major challenge was client drift over rounds. Even with upsampling, variation in local updates caused some mild drift in client models, which highlighted the need for adaptive strategies like FedOPT. Another issue involved edge cases in upsampling. In hospitals with very few examples of rare lesion types, the repeated upsampling of those few images led to overfitting risks. Also, this was a simulated study with only 5 clients. Real world federated deployments at scale, like 50 or 100 clients, may behave differently, both in terms of convergence and stability. And finally, privacy wasn't addressed in this study. Although federated learning inherently avoids sharing raw data, I didn't implement differential privacy or secure aggregation, which would be critical in a real healthcare setting. So, while the results are promising, these limitations open avenues for future work. Finally, let me walk you through the future directions for this project. First, I plan to integrate differential privacy and secure aggregation techniques like DPSGD and secure multi party computation. This will help ensure patient level data confidentiality during training, which is essential for complying with strict healthcare regulations like HIPAA and GDPR. Privacy wasn't implemented in this version of the study, so that's a key area for improvement. Second, I want to move beyond simulated clients and test this pipeline in real hospital environments. That means handling real world challenges like network latency, client dropout, and noisy data. And third, I see a great potential in integrating AI agents for workflow automation. For example, LLM powered agents could help explain periodic predictions to clinicians, auto tune hyperparameters per client, or re-trigger training when concept drift is detected. I plan to use frameworks like LangChain and CrewAI to build those modular and intelligent agents that can assist across the ML lifecycle in a federated setup. So, yeah, that's it. Thank you.
Great. Thank you, Prajinka. I think very interesting master project. I have a couple of questions, and if some of you in the audience have questions, feel free to ask them. We keep an eye on social media to see if there are some questions. So my first question, maybe I missed it when you were starting your presentation. The model you use, is it a pre-trained model or are you training from scratch?
From scratch.
From scratch, okay. And did you consider using other models, or basically did you analyze different type of model architectures, or maybe early in your project you found one that worked well and you continue with
No, so this was actually a very basic demo project. I wanted to just see that how CNN works with federated learning. So this is my first FL project.
Okay.
So I was just trying to see how it works, and I did not use any LLM models or anything. This is or pre-trained models. This is like from the scratch.
Okay. Yeah, that's fine. I think typically a simpler solution is the right thing to do
Yeah,
right at the
in
beginning.
healthcare, I think it is better to use simpler models. If it is like very heavy, then it's difficult.
Mhm. Okay, fair point. My next question is, so I saw you have 5 clients, which I think is okay. I think it's common to have maybe a federation of 5 hospitals. It's not so common to have a federation of 10,000 hospitals, even though that kind of number of clients is something you might encounter in cross-device FL. My
Mhm.
question is, you have 5 hospitals, but why did you also decide to go for 5 rounds only? Maybe in your experiments you saw that turning for longer was not beneficial, or you started to see some overfitting. Can you comment on why 5 rounds?
I think the number of classes were almost similar to the number five,
Okay.
and that was one of the reasons. But yeah, I thought that I don't know, like I just wanted to start with lower number, and because that itself initially when I was doing the FedAVG, that itself was like when I was trying to do the upsampling in that, it started to overfit. So at that time I did not know how to prevent it. So later on I got to know that okay, there is another option for it, FedOPT also. So when I
Mm.
implemented that, it improved a lot. So yeah, I did not actually consider improving or increasing the number of clients.
Okay, no worries. I think it could be interesting to see how the system behaves when you make it a bit more challenging. So, um, yeah,
And
so
also with the yesterday, I think your 1.20 version was launched, I guess. And yesterday itself, I did this project. I mean, the second one, the Fed OPT one. So
oh,
it actually reduced the training time significantly. So earlier it was taking more than an hour, and this time it only took hardly like like almost 19 minutes.
so the OPT experiment, you just did it with the latest version of Flower?
Yeah,
Okay,
yes.
amazing. That's great feedback to see that actually the features are working. We knew they were working, but it's great to. I think you're the first person that I hear experts on saying that it worked very well. So thanks for sharing that. So I have my final question because we are running a bit over time. So you
Mhm.
presented some very interesting points as future work. Are you
Mhm.
planning to work on them maybe as a
Yes.
PhD, or are you starting your research career? Do you have some things you want to share about this, or which of these points you want to tackle first because you had a long list?
I want to like merge 2 points. First is that the I want to include some AI thing into this. So my model till now is doesn't have anything related to AI, but like AI agents or something. Later on, I also and yes, the privacy related things like differential privacy. So those things I want to implement.
Okay. And final question, because I think we have a question on X, uh,
Mhm.
or somebody told me that we have one. Can
Yeah.
you show the slide very briefly of what the model architecture you implemented?
Mm, yeah, this is the one. Sorry, I'm not sharing screen, I guess.
No, you're not showing. I think yes. I remember it was a small CNN.
Model architecture, you mean this one or the
No,
CNN structure?
just the CNN structure. Yeah.
Okay. So this is like a very generic. So this is not
Yeah.
exactly what I am doing,
Yeah.
but this is a generic thing. So this is the actual thing which is
Okay.
present in my.
Okay. So makes sense. Like 3 convolutional layers with max pooling in between, and then two
Yeah.
federated layers. Okay, makes sense.
Yeah.
Um, okay. Yeah. Thank you very much. I think this was great. I think it's super interesting master thesis work. So I encourage you to keep working on federated learning. I think it's a super interesting research area.
Thank you.
Thank you very much.
Yeah.
Okay, I'm going to share my screen because we're going to move on to our next speaker. The next speaker is Jan Ritting. He's joining us from EPFL, and the title of his talk is Federated Learning for Chemical Engineering. That sounds super advanced and exciting, so the floor is yours, Jan.
Yeah, thank you very much. Let me quickly share my screen. All right, can you see it?
Yes, perfect.
Okay, great. Yes, so my name is Jan Rittig. I'm a postdoc at EPFL in Lausanne. And today I'm going to be presenting our project on federated learning and chemical engineering, which I did with my colleague Clemens Kortmann back in Aachen, so at RWTH Aachen University, where I did my PhD. And the motivation for this project lies in the significant increase in machine learning applications for chemical engineering in recent years. In fact, machine learning has been applied on the molecular scale, for example, for property prediction, molecular design, also spectral analysis, and so on. Then also for unit operations, so a bit larger scale, for example, flow simulations, kinetic predictions, also surrogate modeling of specific unit operations in chemical processes. And then finally, also to the process scale. So for example, digitizing chemical process flow sheets, then using generative machine learning to design some new chemical processes, and also, as another example, anomaly detection. So we can see that machine learning has been applied increasingly at multiple scales in chemical engineering. And a major question here is, how can we reach further advances in these fields? So if you look at the machine learning parts, we have typically some data set, a model, an algorithm for training, and then we also need some compute. And to advance machine learning, also for chemical engineering, there are different ways, and then some of them include like improving the data quality, also advancing the models and algorithms, and scaling data sets, models, and compute. And then if we look at the chemical engineering side, so what has been done so far, especially for improving the data quality recently, there's been initiatives on digitizing data, also fair data initiatives, and developing knowledge graphs to structure data. Then for advancing models and algorithms, a big field is incorporating domain knowledge, which is frequently known as physics-informed machine learning, also agents that combine LLMs with chemical engineering tools have been developed. And then for the last part, for the scaling, we know that large models and compute is available, but a big bottleneck in machine learning development for chemical engineering is the limited training data. So we are missing out open source databases, also benchmarks, and most of the data is currently not accessible to machine learning models. So the focus of this talk will be on the dataset scaling, looking at the question, can we scale up training data? And to answer that question, we first looked at the different data sources in chemical engineering. So some of the data we find, for example, for molecular properties is available in the literature. We also have that research institutions have done experiments themselves, and they have data available in their individual databases. Then there's a lot of data stored at chemical companies. Also in software tools, we have some data available. And there are a couple of private data bank organizations, for example, NIST or Dortmund Data Bank, that also have a lot of data, for example, on molecular properties. So if we want to use it for machine learning, like one approach would be to just collect all this data in a database so we can go to the literature, also to research institutions, and the data is openly available. But if we go to chemical companies, also to software tools and the private data bank organizations, the data is locked. So they have this, they put a lot of efforts and labor into actually obtaining this data from experiments, and they do not want to openly share it. So most of the data in chemical engineering is actually locked in data silos. So that's why in this talk or in this project, we wanted to look at a perspective on using federated learning for chemical engineering applications. So replacing the focus on data collections rather on model exchange using federated learning here. And for federated learning, we know these different categorizations of data distributions, and we also look them for chemical engineering. So we have this horizontal data distributions where we have different samples with the same features. And this could be, for example, two chemical companies having data on similar molecular properties. So for example, on the boiling point, but they consider different molecules in their processes. So they have different samples, but both of them have they store data on the same properties. Then the vertical data distribution would be, for example, we have the same samples, but different features. So again, two chemical companies considering or having data on the same molecule, but for different properties. So for example, for the boiling point or for some ignition temperatures. And then the last categorization is the transfer learning one, where we have different samples and different features. And this is quite common also in the chemical industry. So we have companies working on different regions of the chemical space. So this could be one company working more on small organic molecules and the other company working, for example, on polymers. But at the end, these are both molecular domains, and also they are somehow related. So we can also use these relations in transfer learning setups. So what we then did is we wanted to look at the first applications of chemical engineering, of federated learning in chemical engineering, and we looked through the literature. And what we found is that federated learning has already been applied in the process modeling context. So this work goes back to 2022. And here, artificial neural networks have been trained as surrogate models for aluminum electrolysis processes. So data from different Chinese manufacturers have been collected, and then there has been set up a federated learning framework that could then be used to train neural networks for surrogate modeling, and there was an improvement in the prediction accuracy of them. Then federated learning has been used for molecular property prediction, which is a quite active field in many domains, like also in the pharmaceutical domain, for example. Here's one example, the FedChem work, which used graph neural networks for pure component property prediction. And then federated learning has also been applied in process control context. So in this example, a model predictive control, where recurrent neural networks have been used for the control of two sequential reactors without exchanging information between the two reactors. So in this private setup, federated learning has been used. So these are the applications where federated learning has already been applied. And what we then looked at is, okay, where has federated learning also been proposed for? And we found, as one example, anomaly detection, also power and electricity price forecasting, then self-driving labs. And we also then came up with some additional fields, which would be, for example, data digitization. So machine learning, especially convolutional neural networks, have been extensively used for digitizing process flow sheets, which are at some chemical companies still on paper or in some formats that are not directly accessible to machine learning models. So you can use CNNs to detect different unit operations in these flow sheets and then digitizing them. But the problem here is, of course, the companies do not want to share all their process data. So it would be very interesting to use here a federated learning approach that a model can be shared that is trained on different processes, but the process data does not need to be exchanged. Same applies for process design. So generative AI has been used for flow sheet design. So designing chemical processes automatically by reinforcement learning. And again, here we have the same problem. The process data or process flow sheets are not publicly available, especially the ones from the chemical companies. So here, a federated learning approach would also be very promising. Then extending molecular property prediction to mixture property prediction. So not only considering pure components, but rather mixtures of these components would be very interesting. And lastly, another very important field in chemical engineering is risk assessments. So we have this so-called hazard and operability studies, which are text-based and also can include multimodalities. And here, for example, large language models have been used to automatically assist in the generation of these studies. But again, like these studies are confidential, and because they include security information about the processes, so they cannot be openly shared. Again, here federated learning would be interesting to train these models. And what we did in our project to investigate the potential of federated learning for chemical engineering applications, we considered 2 different case studies. And the first one was about process modeling. So in this process modeling case study, we consider a distillation column. In essence, what we have 2 different molecules here, and they're in a mixture. So we want to use a distillation column to separate them. So here's a schematic illustration of the distillation column. We have the mixture as the input, and then ideally we separate these 2 molecules, and we have like different inputs. So the feeds of the mixture can vary over time. So the composition of the molecules within the mixture can change. And what we model then is the system dynamics. Like if, for example, the feed composition changes, like how does the distillation column behave in this case? And then we have different parameters that we can change in these distillation columns. And one of them is this vapor flow rate here indicated with V. So if we have different vapor flow rates, also the system behavior of our distillation column will change. And it's challenging to model the system behavior. So what has been proposed by a colleague also from Aachen is to identify low-dimensional models to predict these dynamics, specifically by using these kind of autoencoder structure in combination with Koopman theory. I will not go into the details. We just need to know here there's a machine learning model which tries to model this system behavior. And to simulate a federated learning scenario, so we came up with this general challenge, which is that companies operate similar distillation columns, but under different conditions, and they typically also have limited data. So what we said here, we have 4 different chemical companies. They all operate the distillation columns, but at a different vapor flow rate. And they have already collected some data from their processes based on the operation of these distillation columns. And then we have a 5th company, which just has installed this new distillation columns, and they only have very limited data. So the idea is here that we can use a federated learning setup so that the companies can contribute to the development of these machine learning or these autoencoder models, and that the 5th company, even though it only has very limited data, can benefit from the experiences of the other companies without the need to share these data points. So the goal is here few-shot learning for this target process of the 5th company. So to simulate this scenario, what we did, we first created a data set with these different vapor flow rates for the individual clients, which are indicated in the different colors here. And then we compare 3 different scenarios. So the first one is that the 5th chemical company only uses the individual data and trains an individual model on that. Then we have this federated learning setup where we have the 5 companies collaborating and exchanging the models, and we implemented this with the Flower framework and called this scenario the federated few-shot learning one. And then as a baseline, we just imagine that the 5th chemical company has a data set of the same size as the other companies, just to compare like what would happen if the company had collected data on their own. And here we can see the results. So in this plot, we can see the test mean squared error of this machine learning model for the 3 different scenarios. And what we can see here is that the baseline model, like if the 5th chemical company had collected data on their own, compared to the target few shot, so where it only uses individual data, has a much lower error. But if we then apply this federated learning scenario where the companies exchange the models, we can get a similar error, even though the 5th chemical company has not collected any additional data. So in this case, the federated learning highly improves the few shot system identification of the distillation column, and is just highly promising in this case. And then as a second case study, we investigated mixture property prediction. And again, here we can start from the scenario of having a distillation column, but this time we're not looking at the system behavior, but rather look inside the distillation column. So we have these 2 components, and they somehow interact with each other. And we can use the concept from thermodynamics, which we call activity coefficients, which gives us some quantification of the non-ideal behavior of this mixture. So because this activity coefficient is needed for separation processes, it's very interesting for many chemical engineering applications, and it's highly desirable to predict these activity coefficients. So we have been developing machine learning models to predict these activity coefficients, and they are based on graph-based machine learning. So we start with the molecular structure, then we create these molecular graphs, and then we can use so-called graph neural networks, which give us first an embedding of the molecules. We again can employ GNN to give us some mixture representation. We can also use some additional features such as the temperature of the mixture, and then use the standard multi-layer perceptron to predict these activity coefficients. So again, we do not need to understand the details of these models here, but in general, we can use machine learning models, in this case, graph neural networks, to predict activity coefficients directly from the molecular structure. But again, a big problem here is that obtaining these activity coefficient data is very costly because we need to do lab experiments. So in a realistic scenario, we would have like different chemical companies having obtained activity coefficients for different chemical compounds or for different chemical species. And they, of course, do not want to share this data because it's very costly, but they all want better prediction models. So the goal here is to advance activity coefficient prediction without sharing the data. So we investigated here a federated learning scenario where the companies decide to collaborate to jointly train machine learning models for it. And we here came up with two different setups. So in the first one, we just assumed that the activity coefficient data is randomly distributed among the companies and that they decide to share the whole model. And in the second scenario, which is a more realistic one, we assume that we have a scaffold-based data distribution and that only parts of the models are shared between the companies. So looking at the first setup where we randomly split the data, so we have this chemical space, we just randomly split it, and here we used a data set that is openly available to simulate this federated learning scenario, and we separate it into 4 chunks of equal size. And then we set up this federated learning framework using Flower that is used then to train the different graph neural network models. And for the individual data sets, we split them into a training, validation, and test set, and we report the average accuracy over the test set and repeat this for 10 runs. And as a baseline, we here use a graph neural network that is just trained on the whole data set. So just combining all this data in one data set, and we call this the centralized scenario. So the question that we here wanted to investigate, does federated learning provide a benefit for the clients? And here we can see the results for this first scenario. So we have again the test mean squared error of the machine learning model over the number of communication rounds of the federated learning training. And here the first round corresponds to like only the individual companies training their own model. So what we can see here in black is the centralized scenario, which has a constant mean squared error over all rounds because we just train it for one round. We use the whole data set. And then we have the global model of the federated learning and also the average client model, so the individual models that are trained on the individual data sets after each or in each round. And the interesting thing is that we can see here is that by using federated learning, and here especially the global model that is shared among the different companies, we can see that after about 30 communication rounds, we get a similar error compared to a centralized model that is trained on the whole data set. So even though the companies do not share the data and only train always on 25% of their individual, or using 25%, so their individual data set, we can see that federated learning enables the clients to achieve a similar performance to a model that is trained on the whole data set. So we saw that this is very promising in this scenario where the data is randomly split. And then for this more realistic scenario, we assume that the chemical space is separated based on scaffolds for the different chemical companies. So each company works on a different region of the chemical space. And what we also assume is that the companies have different sizes of data available. So one company, for example, has 40% of the data, while the other company only has 10%. Again, we report the average accuracy on the individual test sets. And we use a federated learning setup here with the shared model training. But what we assume here is that only this first part of the model is shared, while the other part, so this prediction head, remains private. And we use here the FedPer algorithm to train these models. So the question that we were interested here is, does federated learning also provide a benefit in these more challenging settings? And here we can see the prediction error. So again, the test mean squared error over the number of communication rounds for the individual clients. And the first thing is that we can observe here is that federated learning leads to model improvement for all the clients. So we can see a knowledge transfer across the chemical space. And if we now look at the individual clients, we can see, as expected, the client with the least data available, so only 10%, benefits the most. So the relative improvement in the accuracy is about 60%, while for the company with the most data available, so the 40%, we can see that the test accuracy only increases by about 17%. So in general, as expected, clients with less data benefit more than clients with more data. So what we conclude from that is that's definitely important to create incentives for the different companies to participate in this federated learning collaborations. Yes, and with that, I would like to summarize. So we have seen that federated learning is largely underexplored for chemical engineering applications. And so we contributed here to identify promising chemical engineering applications for federated learning, and also proposed federated learning for system identification and mixture property prediction. And as limitations and next steps, it would definitely be important to look further at the heterogeneity in chemical engineering data. Also consider data extraction for models, especially for the molecular domain. There has been some recent work on that. And also creating incentives based, for example, on game theory, due to the reasons that we saw on the last slide. And definitely for practical considerations, it's important to account for computational infrastructure, cybersecurity, model and data poisoning, and so on. And with that, I would like to thank you very much for your attention. You can also find more details in our recently published paper here. And yes, I'm happy to answer any questions. Also, please feel free to reach out afterwards. Thank you.
Thank you, Jan. I think this was a super interesting and very well delivered talk. I like the slides, like particularly slide 4. I think it was 4 and 8 were super good when you were presenting what's the problem with the data. There are some openly available data sets, but there are many sources of data that are locked, like the labs and things like that. So I think it was described super well for all audiences. I have some questions. I know that some details you skip them because I think they are super relevant, but can you give a little bit of insights on, especially for those that are familiar with working with molecules, what were the features you consider to extract from the molecules themselves? Were you using SMILES? I saw you were using PyTorch Geometric. Maybe you can give a bit of what type of GNNs were you implementing here?
So here we used, as you say, we used some GNN implementations which are based on PyTorch Geometric. So in my PhD, I developed kind of my own framework for molecular property prediction, which is applicable to pure components, but also to mixtures. And we typically start from some molecular representation, which can be, for example, SMILES, and then we transfer it to a molecular graph using a DKIT. And we use here some standard features which have been used in the molecular domain when using graph neural networks. I think the interesting part here, especially for the mixture property prediction, is like typically what you do for pure components, you have this molecular graph, then you have this GNN, get the molecular fingerprint, then predict the property you're interested in. But for mixtures, what you can additionally do is you represent basically the mixture as the graph itself, because you have like the different components being then the nodes and then the molecular interactions being the edges. And you can use these molecular fingerprints then as the node features. And for the edge features, you can then use some molecular interaction descriptors. And then you can apply again a graph neural network to get the mixture embedding, which can then be used for this final prediction.
Can you share how? So my experience with GNNs is limited, also back from my PhD, but only a small part of it. Can you describe a bit, give some high-level metrics on how big these models were and what was the size of the typical molecule you were working with? The size of the graph, basically.
Yeah, so I do not know the number of parameters by heart. I think it's in the range of 100,000.
Okay.
It can range it depends very much on the type of graph convolutional layer you use. I think in this case, we use the Gine convolution. And for the molecules, we typically, in this case, considered like this data set, which I highlighted here, is a publicly available data set on activity coefficients, which is mostly on small molecules used, like in the chemical process industry.
Okay.
Yeah.
Good. I just have one question. So in this here, what you're showing now is like the random splitting. I think it's very easy to understand. Can you give maybe just for the audience, like what is, and also for me, what is the short summary of what is scaffold-based partitioning? What is this clustering
Yes.
based on?
So in scaffold-based splitting, what you typically do is you consider like some kinds of scaffolds which are present in the molecules, and then you try to find clusters of molecules which have similar scaffolds, so which can be, for example, some subgroups of or functional groups of the molecule. And there are a wide range of different scaffold clustering schemes, but in like on a higher level, what you can expect is that these separate the molecular space into different regions of molecular structures with similar functionality.
Okay. I think that makes sense. And you think it's realistic that for example, some labs, based on your experience, some labs would focus on some particular molecule structure space?
Yes, so I think like if you go to large chemical companies, of course, they work on different regions in the chemical space. But you will still have a focus on specific compounds, also if they investigate like different versions or small changes in these molecules and check like what are the properties. I think you can assume that like this chemical space is distributed then for these companies a bit, and they look at specific regions in the space to see whether these molecules can improve with small changes.
Mm-hmm. Okay. And just final question I have here, I think it was slide 20, towards the end, you were talking about the incentives. And we can see here that one of the client that has the most data, it gets a relative reduction of only 17%, which probably is still very good on itself, but is not as much as the others. Do you have some thoughts, or have you been in discussions of what could these incentives look like, in particular for the molecule?
Yes, so good question. So we have not investigated this in detail. I think it's very important to have some kind of incentives in the sense of like what does or how do you value the data that is contributed to these federated learning setups? And I think one option would be to have it like in a monetary way, like companies that provide more data or lead to larger models improvements of the others, like get some kind of money for it. Or you could also, for example, say that the number of model calls or is constrained, and then that the companies that contribute more also can use the models more or get some other kind of benefit from that.
Yeah, I think that one is interesting. I've also heard similar ideas, like if the resulting model lives maybe in a third-party server, then you could control its usage based on how much data, for example, each entity put towards the training.
Exactly. Yeah.
Interesting. I'm getting here some questions from X. I will just read the question.
Okay.
Just curious, have you looked into multimodal data for federated learning in the chemical engineering applications?
Not so far. I think in general, like multimodalities for multimodal machine learning for chemical engineering applications have not been investigated too much, but I think it's very interesting. Like you have different scales in chemical engineering, but also like process descriptions vary from like images of the process flow sheet, but also textual descriptions. So it would definitely be interesting to investigate this further. Yeah.
And one final question, we will wrap up. From LinkedIn, it's a broad question, but maybe there are some interesting maybe you have some interesting ideas. How can we implement basically this federated learning with molecules for a more real life health use case? So here's more like processes in labs, but is there something that can be done maybe for more everyday usage?
I'm not sure what is meant by more everyday usage.
Yeah, I'm not sure either, but well, we try. I think that's okay.
Okay.
Yeah. Okay, well, thank you very much, Jan, once more for your presentation and for answering all these questions. I think this was super interesting. And if anyone out there is interested in Jan's work and all the research behind it, be sure to check his paper.
Thank you.
Thank you very much. And now let's jump to our next and final talk. It's going to be given by William. He works with us in the Flower Labs team, and he's going to give a talk titled Community-Driven Projects Using Flower. So, William, the floor is yours.
Yes, thank you. So we already heard so many, like these two great presentations, and this will basically be a shout out to the amazing researchers and professionals out there working with Flower to realize their projects. But let me share this one. I think you'll be able to see it right now.
Yes, we can.
Perfect. So let me click through. Yes, at Flower, we try to make sure that it's a plug and play framework. Basically, you should be able to use whatever you want for your federated AI applications, whether you want to use, run it in experimental mode or put it into a larger scale deployment, but you can also run it with various models for various data types, and you can also run it on different sort of devices. So this is very probably interesting for people working on lower tier devices, not only bigger GPU clusters and so on. So this is what we are actively working on at all time, and you are more than welcome to suggest any sort of improvements. You can find us on GitHub, Slack, go to our website, flower.ai to connect with us, and we are more than happy to chat with you. And these are just some of the numbers that we are very proud of. We are happy for any project that is built on Flower or people coming with ideas. So if you want to be one of our active contributors to the open source framework, you can also just go to Flower on GitHub and connect with us there. But some community-driven projects, well, we are in Flower Monthly right now, and it's been going on for a while, and we've seen so many great presentations over the last years. So if this is your first time, make sure that you tune in to the next ones, spread the word, because we always try to, emphasize really cool use cases and people building on top of Flower. So make sure that you, tune into these. Also, one of the recent contributions is FlowerTune LLM and the leaderboard itself. And why I'm bringing this up is, yes, it's built together with the Flower team, but what it allows you to do is that you can benchmark different models and you can fine tune them in a federated way and test them on different sort of tracks. So you can fine tune them for general natural language processing, for finance task, for medical stuff, and also for coding. And this is we have seen so many contributions from researchers out there testing out models, fine-tuning them in a federated way, and then benchmarking them on acknowledged data sets, basically. So if this is something that speaks to you, feel free to check this out, because over the last couple of weeks and months, we've seen a large increase in this, and it's great because it really showcases, okay, what models are good in terms of maybe metric performance, but also we look at communication cost side of things. So feel free to check out the leaderboard. It's up there. You can select the categories that are shown here. And here are just some numbers that we've seen. So in performance, like you can find more information on this as well, but we see increased performance with federated fine-tuning, also drop in communication costs depending on the model that you are using. But you can find all of this out there, and this is actively contributed by great researchers out there who are interested in supporting Flower and just testing it out for themselves. So take a look at that, flower.ai, and you'll find it. Then I wanted to highlight some recent ones that sprung up from finance. So we actually had researchers at these organizations here at AWS working on fraud detection, and it was powered by Flower. It's a really cool integration together with their Amazon SageMaker AI. So you can find a whole blog article online on this. But this is just one way of using Flower in for example, fraud detection. It's a big use case in the finance industry, and federated learning could really help there. Similarly to on the right, we had Kinexus, I think you say it, but by JP Morgan and BNY. They did something in the same way that, the details of the different projects are different, but it's about anomaly detection, fraud detection, things like that goes on for financial transactions. So federated AI fits very well into this. And if you're working in the finance domain, you might also want to check out a bunch of papers that build on top of Flower. These are just some of the kind of ones that I could find online looking quick. And this is only from 2024, mid 2024, I think. Maybe one was from 2023, but they're fairly recent ones, and I'm sure there are more out there. I just wanted to highlight this. So finance is one application area that you can use Flower for. We have great models. We just came out with a new model, the CatBoost example. If you like working with structured data, you can use the CatBoost. You can also use XGBoost, another great model, and you can develop your own models for this as well. Feel free to chat with me there. I'm very interested in these sort of models, and I'm sure that we can build something great. But I just wanted to highlight these studies here because I think this is a great testament to what researchers out there are building. So thank you very much for citing Flower in this. Then also healthcare. We've heard about healthcare earlier, and I just wanted to highlight some that have been developed and worked on throughout the last year. So one of them is federated AI in medical imaging. This is a privacy-aware solution that is built on top of Flower, and Adway from University of Maryland. He recently published it's federated learning using partial labels, which basically means that at different hospitals, you might not have access to the exact representation of, let's say, a kidney or something like that, or the brain scans. So you want to collaborate, basically speaking to the fundamentals of federated AI and why it's such an essential part in this. He did great work on this. Worked together with our team and published the research out there. The other one is Eye2Gene, which the team is doing retinal scans, checking for eye diseases, and they built a global federation on together with Flower for basically scanning eyes, retinal scans of your eyes to check if there are any diseases out there. And you can see the countries that were involved. They're working actively on this. So this is one of the really cool use cases in healthcare, I think. But another one is one that Javier has been working on together with. This is blood counts, and this is for blood analysis, basically. This is also a global project at this point where they are working on analyzing different sort of blood samples and making it a privacy-aware solution through federated AI and Flower. But same thing here, a lot of research is out there on federated AI in healthcare built on top of Flower. I just retrieved some here from the last year, basically. But this is definitely a very interesting area if you are, building in healthcare, think that Flower would fit well, we are always happy to chat about this. So shout out to all these great researchers as well. And as we have seen, there are more fields to it. We heard about chemical engineering as well, but there, I've just scanned Google Scholar earlier, and you find articles in robotics, general AI, also energy systems, automotive, defense tech, IoT, agriculture a lot, which is very interesting, and robotics. So to everyone who's building on Flower and wants to chat with us, feel free to do so. Go to our GitHub, Slack, ping us there, and we'll be happy to talk more about it. But definitely big up to all the great professionals and researchers working on Flower, or working with Flower. Then just lastly, I wanted to highlight a different one. It's kind of community type of thing. It's a work that we do together with Vana at this point. And Vana is a decentralized platform where user can actively share and monetize their data. And on top of this, so they basically own their data rights, you could say. And we, together with them, we are introducing the Collective One. So this will be the first decentralized user-owned foundation model that you can use out there. It's actively being worked on. And you can think of it as a community thing if you think of the decentralized platform where people actually share and own their data to this. So these are some of the specs that you can expect. Might be slightly different, but hope that we can bring it to you very soon. And don't forget, Flower AI Day is also coming up. So if you want to connect with the whole team, check us out there. That's it.
Great. Well, thank you for all this great overview, quick overview on some of the many projects that are out there built on Flower. Many of these have already been presented in the Flower Monthly, but some of them haven't. So if you are, watching the live stream or you're watching this session later, once we publish it, and you want to present some of your amazing projects in Flower Monthly, just reach out to me or to William. We are in Slack all the time, so it's very easy to ping us. I have one question. Could you give us maybe a small preview of what to expect on the Flower AI Day? Is there anything we could share at this point, or are we sharing this later?
There might be some hackathon going on in that way or something like that.
Oh,
So
sounds-
if people are interested in doing some intense, I don't know, one-day work and supporting what we do here, then feel free. There might be some rewards as well. So definitely go check that out. And yes, if you just want to talk about whatever project you're building, then you can join us there, chat with the whole team. The whole team will be there. So you just pull one aside and talk with us about whatever you're working on, and we'll be happy to discuss it further.
Okay, great. Yeah, I think that's a super exciting event. So thank you very much for the highlights on all these projects, William.
Thank you.
So now that we are finished with these 3 amazing talks, it's time to wrap up this Flower Monthly. And as you know, every Flower Monthly happens on the first Wednesday of every month. Next month is September, which means that the year is approaching to its end. So it's going to be on the 3rd of September, same time for UTC, same place, Zoom, X, LinkedIn, or YouTube. We can't wait to have you there next time. Again, I want to stress, if you're excited about meeting the team in San Francisco late in September, feel free to book your slot by going to flower.ai. This is a Luma event. So yeah, check it out and see you in 4 weeks. Bye-bye.
Bye.
By going to flower.ai.
Bye.
This is a Luma.